Marcel, please.
Thanks. It's a bit bright here, but you look very pretty. Okay. So it's a serious topic, so I would like to ask you a few questions. Did you just recently maybe have a breakup? Do you feel lonely? And are you looking towards a long-lasting relationship, but you actually don't know how to get there? Well, this is actually the right talk for you, because what I do in the lab is couples therapy for molecules. So let me ask you a question first. Who here is in a relationship? Who is in their first relationship? Anybody? Okay, nobody ruined it for me. Okay, no, there. Okay, so if Svenja from kindergarten does not count, I am in my first relationship, and that means I can try to teach you something about it today. All right. So what are my qualifications? First of all, I'm a great husband. And second of all, I'm an awesome father. But also, I am a cold atom and molecule physicist. So there's two aspects to this. So first of all, my heart and soul is in this topic. But also I'm trying to look for empirical evidence to find out what makes a good relationship. But before I start talking about my great method, I must first give a disclaimer. I was specifically asked to do so, to tell you that the information presented in the Science Slam does not mean to be any psychological advice, nor any of the treatments listed herein. Always consult a professional relationship counselor. So what's the approach? So I recently found a publication where the authors were trying to use machine learning to identify what makes a good relationship. And they found two categories that are very important, namely the specifics of the individual. So for example, the age, whether somebody has a depression, or maybe whether somebody has a lot of stress. But also what they saw is, or what they think, is that relationship-specific attributes are important. For example, affection, or I don't know, how the partner is perceived, or children. Yeah. So, of course, there's these many vices and virtues, but as we call it as physicists, parameters, and they're much too complicated for us. So actually, I would like to study a very particular relationship to boil it down to only very simple kind of properties. So, what do I mean? Well, I have molecules, and these molecules are composed of two atoms. In my case, it's a sodium atom and a potassium atom. And the sodiums, we call them bosons. For those of you who are not physicists, let's call them bisexuals. And they look like this, by the way. And we also have another type of atom, the potassium, which is a fermion. And we call that one heterosexuals. They look like this. And so we are specifically in our lab, we are studying this type of relationship. There's many other relationships that you can also study. So why am I talking about the bosons and the fermions? Well, what you should keep in mind is if a boson is close to a boson, that's okay. If a boson is close to a fermion, that's also okay. But if a fermion and a fermion comes close by, well, they don't like that very much. So for example, let's see, there is a fermion over there. And I say, hi, fermion. And now I want to get a bit closer, maybe a bit touchy. Oh, no. It doesn't like it. Okay. Well, let's stop here. Well, this is the experiment that I'm working with. And what you can see is we have these kind of oven sections. This is where our potassium lives. This is where our sodium lives. And they're at about a temperature of 100 degrees Celsius. And we use lasers to cool these atoms down to temperatures that are much, much, much colder than what you're used to, maybe 1 billion times colder. And then what we do is we look at them in this kind of glass cell. But I was told that I shouldn't brag about my experiment. So let's just imagine a little bit differently. We have atoms and then they're in a very cold place. Ischgl. And let's hope they don't get corona. And in Ischgl, there is something like an après-ski party. Okay? And those of you who are not German or Austrians, an après-ski party is, if somebody tells you, I like to go skiing, what they actually mean is, I'm okay with skiing, but actually I want to get drunk afterwards. So at this après-ski party, this is where we have our atoms. But before, so I told you I will study relationships, but before we actually want to study these relationships, we first have to make them. Because we have these two atoms, or many, many atoms, that actually first want to be made into couples. And so what you can see here is a magnetic field. This is something I can control in my experiment. And you see two different lines. Unfortunately, one of the line is not visible right now because of the projector. It's somewhere here. And this dashed line is the energy of the atoms, and the line that you cannot see is the energy of the molecules. And where these lines meet is something called a Flashback Resonance. This is where we make our molecules, or as you guys call it these days, Tinder. So when I take my magnetic field and I reduce it, the atoms can make a choice. Either they swipe to the right and they decide that they want to be atoms, we don't want to be couples, how sad. Or they decide that they want to be molecules. And what I can do is, when I'm changing the magnetic field, I can actually change also the binding of these molecules. So at these magnetic fields here, the molecules are far from each other. If I go to lower magnetic fields, they come closer to each other. And the energy difference, again, you cannot see it, is defined by the binding energy. And what's particularly interesting about this is, as the relationship becomes closer, as the binding energy increases, not only the fermions become aggressive to the other fermions, but actually the couples say, we don't like the other couples. So my method of making couples is not 100% successful. So the people that work at the après-ski party, actually they say, let's do night out for the couples. So we have to kick out all the singles. Remember, I want to study a simple system. Having singles in there would just make it more complicated. So there's two types of encounters that I have between my molecules. One is called an elastic collision, as it's demonstrated with these billiard balls, which means that the molecules come close together and then they leave again. I mean, you can think of it as two couples come together, they maybe have dinner, they play a game of Dixit, and then they leave again. But then there is a different encounter called an inelastic collision. So it's illustrated by these cars that crash together and they deform, heat is produced, and there is a sound. And this is actually what we are looking at. And what we see when we are looking at these inelastic collisions is something called loss. The molecules just disappear from our side. So how does an inelastic collision look like in our experiment? Well, two molecules come together, then they form a threesome. One of the fermions, because it doesn't want to be close to the other one, doesn't like that very much, and it leaves the party. But the threesome, as much as I mean, you might enjoy it, but actually it's not a very stable thing. So afterwards, they also break up, but because this was such an important moment in their life, they also leave the party. So let me now show you the data, because we actually probed this in the experiment. So this is again our curve. There's again the line that you cannot see. And we are now trying to look at the relationship at this point. So what you can imagine is that the molecules are very weakly bound. Maybe you don't really want to consider them a relationship, but they actually are. And if we hold the molecules for some time, you can actually see that the number of molecule drops. Now we probe the number of molecules as a function of time when the binding energy is much larger. So the binding energy would be something like this. And what we see is that the molecules live much longer. So what do we learn from this? Well, first of all, if your relationship is not strong enough, stay away from other couples. Second, the larger the force that keeps you together, the more you realize your relationship is no different than any other. And last, long distance relationships don't really work, at least not for long. So, You might think, this is very simplistic. Why are you showing us this? And I say, well, first of all, I told you we want to study a simple system. So next time we meet, we can also have a look at what happens when partners and singles start to mingle. Thank you very much.
Marcel Duda!